Hello everyone, my name is Watson. I am a student researcher here at CBBG, the Center for Bio-mediated and Bio-inspired Geotechnics, here at Arizona State University. So today I'm going to be demonstrating a small experiment showing how liquefaction can be mitigated. So usually in a regular sand, when there's earthquake, the sand particles are tightly held to each other, so they don't move. They shake, but they don't move apart. But if the sand is filled with water or saturated with water, when there's an earthquake, it kind of moves apart and the thing on the top just sinks in. So imagine having a building on the top of a saturated sand. It's going to sink. It's dangerous. So today I'm going to be explaining how we can mitigate this in real life. So here I have two bowls with sand. Both of these have water. This one has a little bit of water and this one has a lot of water. It's basically saturated with water. So I'm going to try to put the steel ball inside one of these which has a little bit of water and try to mimic an earthquake. See what happens. You see, this one shakes, moves around, but never sinks. But here, when we come to a saturated soil, that was quick, just went inside.
So now that we know what liquefaction is, let's take a look at what it looks like on a little bit bigger of a scale. What I have here is a machine that's going to simulate an earthquake in this liquefiable soil. So let's pretend that this big thing that I've got here is a building. And we've built this building on what we think is some solid ground, but we don't actually know that this is liquefiable soil. Now here comes an earthquake. And what do you think is going to happen to the building when the soil turns to liquid? I wouldn't want to be the guy who paid to have this building built. So to add on to that, what do you think would happen if we put something lighter than liquid, like a ping pong ball or a football, in this sand? Now here comes the earthquake. Notice how they just float right to the top. Because they're less dense than the sand, and the sand is now a liquid, these buoyant things can just float right to the top. So as you can imagine, when an earthquake happens and you've got buildings built on a soil like this, it can cause a lot of damage. Here at the CBBG, we're working to find solutions to these problems, whether it be cementing the ground with a nature-inspired cement, or adding a crust to the soil so that the building doesn't collapse. Can you think of any solutions that might help this problem?
Hi again. Here at the CBBG, we find ways to solve problems innovatively. We use inspiration from nature. So why don't we take this soil liquefaction problem? We already saw what happens when we place a steel ball on fully saturated sand. It sinks. And when we place it on slightly saturated or just a little bit of water in the sand, it just stays on top and it bounces around. I wouldn't want to be in either of those buildings if an earthquake were to happen. So as geotechnical engineers, or engineers who work in, on, and with the earth, we've come up with solutions. And here at the CBBG, we take inspiration from nature. So why don't we take a page out of our handbook and add a little bit of our hydrogel, our water-loving, to our experiment and see what happens when we place our steel ball on now. So here comes our earthquake. This time, our steel ball moved around because as the water moved up through the soil, the hydrogel absorbed it, preventing the soil from liquefying. And in our other example of an unsaturated or just a little bit of soil in our water, we show that if we just take out just a little bit of water, we can solve our problem and we won't have liquefiable soil. What other things can you think to add to prevent soil from liquefying?